So we looked at how to find slope, or dy dx, for a function that's defined parametrically. And I just wanted to look at how you would continue on if you wanted a second derivative or third derivative or any higher order derivatives. And the idea is to just use this definition again. And the way to think of it, so here we saw that to get slope, you just take dy dt over dx dt. Now, what would that mean to take the second derivative? Well, this literally means the derivative of y prime with respect to x, right? So if we look at this formula as saying you're taking the derivative of y with respect to x, so you have to take the derivative of y with respect to t over x with respect to t. Well, the only thing different now is instead of that being y, it's y prime. So we need to take the derivative of y prime with respect to t over dx dt. And we could continue on in this fashion, right? If we wanted the y triple prime, well, that means take the derivative of y double prime with respect to t. So that means take the derivative, nope, sorry, with respect to x, right? Misspoke. So we're going to take the derivative of y double prime with respect to x, which means take y double prime with respect to t over dx dt. And in general, to get whatever derivative you want, it'll be one less there. Right? So if you want the 10th derivative, it'd be the 9th derivative of y with respect to t over dx dt. But the key is that bottom is always dx dt. So if you wanted the n plus 1 derivative, it would be the nth derivative of y with respect to x is what we mean. Which would mean the nth derivative with respect to t of y over dx dt. Now, one of the things people often wonder when they first see this is, why aren't we taking higher and higher derivatives of x as well? It seems like we should be maybe having x prime here, x double prime, x triple prime. But if you think about it, that wouldn't make sense. What does it literally mean? If you look at this, I think it helps. A second derivative means you have some function y as a function of x, right? You vary x a little bit, you see the change in y. If you want the second derivative, you vary x a little bit and see the change in y prime. If you want the third derivative, you change x a little bit and see the change in y double prime. So you're only ever changing your independent variable, x, and looking at the reaction, if you will, or the rate of change there with respect, the ratio there with the dependent variable. And so what's changing each time is that function, right, is now y prime, y double prime, whatever. But you're only ever just changing that independent variable. That's why this is always just dx dt on the bottom. So let's do an example. Say we had one of our circles. X is sine t, y is cosine t. Maybe sketch a picture here. Remind ourselves, that's a circle centered at the origin, radius 1. And at time 0, x is 0, y is 1, so you're right here, right? So this is the one that goes clockwise, right? So let's pick a time. Maybe let's do this at a specific point. So maybe we'll let t be, I don't know, say 3 pi over 4. OK, so let's find the first and second derivatives. So we've already looked at first derivative. To get y prime, you want the derivative of y with respect to t over derivative of x with respect to t. So there's y. Derivative of cosine is negative sine. And derivative of sine is cosine. So what we have is negative tangent. All right, that would be the slope at any time t. We were interested at 3 pi over 4. And really, I probably shouldn't use this function notation, right? This implies y as a function of x. That makes it seem like I'm saying x 3 pi over 4. So I'm going to use the more explicit notation like that. So it's clear to the reader that I'm taking that first derivative and I'm evaluating it at t equals 3 pi over 4. So that's negative tangent 3 pi over 4. Tangent of 3 pi over 4 is negative 1. So we have negative 1 or 1, which makes sense because we're talking about that line, slope of 1. Seems reasonable. OK, what about y double prime? So we're going to take what we found before, y prime. Notice y prime is a function of t, so that makes sense. Derivative of y prime with respect to t, it's already a function of t. So y double prime means take this function and differentiate it with respect to t, y prime with respect to t. So derivative of tangent, secant squared. So it's negative secant squared over, and again, it's just dx dt again. So derivative of sine, cosine. And 1 over cosine is secant. So what we really have, we can write this as just negative secant cubed. And what is that at t equals 3 pi over 4? Well, it might be easier to think of it actually as over cosine, right? Because we're more comfortable with sine and cosine. So what we have is negative 1 over cosine cubed at 3 pi over 4. Cosine's negative at 3 pi over 4, right? So that's negative root 2 over 2. So we have negative 1 over negative root 2 over 2 cubed. Cubing will still leave this negative, so we'll have a negative on top and a negative on bottom, so positive. 2 cubed is 8. Square root of 2 cubed is 2 root 2. So I have 1 over 2 root 2 over 8. If I flip that, the 8 will cancel with the 2, and I'll just have 4 over root 2. Or if you want to rationalize that, root 2, this is 2 root 2. Does that make sense? What does y double prime tell us? Y double prime tells us concavity. And at this part of the curve, we are smiley face, right? Concave up. So we should expect a positive value. Now, whether that actual value itself makes sense, it's a little bit harder to say, but definitely being positive makes sense because we're concave up at that point. And you could continue on. If you wanted the triple prime, you would take double prime with respect to t over cosine again. And then the derivative of that over cosine, the derivative of that over cosine, you could keep going through these derivatives.